Example, we have a very simple goal. We would like to estimate the average downloads per month from like a streaming service, music streaming service like Spotify or Apple Music. What are the average downloads per month? So to get that answer, you take a sample and you look at the average from that sample and you use that average as a measure of the population value. What would be the true average downloads per month for everybody, not just the sample. So in this particular case, we have a sample of 100 and we find an average of 2.0. So sample size n equals 100 and the sample mean is 2.0. And in that sample mean, we find in that sample we find a standard deviation of 1.0. So what we would estimate is that those values correspond to the whole population, that the population mean is 2.0 as well, and the population standard deviation is also 1.0, just like the sample. We use the sample to estimate the population. However, we want a better answer than that. We want to know how well the sample represents the population, and like how precisely we can narrow down the population value based on this estimate from the sample. And the way we do that is by building, or one way that we can do that is by building a confidence interval. And that is by taking some number, and we call that number either the margin of error or the error bound. It goes by different names. But we take that number and we add it or subtract it from the mean value. That gives us an interval, and that interval we call the confidence interval. And it has a percentage associated with it, like our percent confidence level, and that part is kind of arbitrary. Like if you want to be 100% confident, you can give a very, very large error bound, and the result isn't very meaningful. And if you give a low confidence interval, you can give a very narrow error bound, and that's not very useful either because you're not very confident in the answer. So often the default is 95% confidence. We know from studying normal distributions that 95% of the data is within 2 standard deviations. So we're really looking at like a 2 standard deviation range. And because we're talking about the distribution of the sample, we're talking about the sampling distribution, that means we mean a 2 standard error range. So here we're calculating the 95% confidence interval for this particular example. And we have a mean of 2.0 and a standard deviation of 1. So we calculate the error bound for the mean by doing 2 times 1 over square root of 100. And so this part right here, that's the standard error of the sampling distribution. And 2 times that value gives us like our 2 standard error range, and it corresponds to 0.2 in this case. So that's our error bound for this mean value is 0.2. So if we go 0.2 below 2, 0.2 above 2, that gives us the interval from 1.8 to 2.2. And we fully expect that 95% of samples would fall within this range. And so that's our confidence interval for the mean value downloads per month. However, there is something more we could think about here, because when we estimate the standard deviation, we're not totally sure that that's actually the right value. And so we're really estimating 2 things at once. We're estimating the mean using the sample mean, and we're estimating the standard deviation using the sample standard deviation. So to give a more precise, better answer, we need to think a little bit more about the distribution that we're using. So using the normal distribution, we get 1.8 to 2.2. But what about that extra uncertainty because we're estimating this value? Well, to account for that extra uncertainty, we can change from a normal distribution to something called a t-distribution. And that t-distribution is just a little bit wider in the tails. And so it's going to make our interval a little bit bigger. And it'll account for that extra uncertainty when we estimate the standard deviation as well as estimate the population mean. So what happens in the calculation is what we just did, or the idea we were just using is right here. We take the mean, we take the z-score, and because we wanted a 95% confidence interval, we used z equals 2. And then we would put in the population standard deviation here. If you're also estimating this value, and this isn't sigma, this isn't the population standard deviation, but instead it's the sample standard deviation, then we're going to change from a z-score to a t-score. So everything else is the same. We're using the same sample mean. We're using square root of n because it's a standard error. But we're going to change this number from a z to a t to account for the fact that we don't know the population standard deviation. We know the sample standard deviation. And just like before, we would have a confidence level that's associated with this. And so let's take a little look at the t distribution. All right, so the dotted line here corresponds to a normal distribution. The t-distribution looks a little bit different. Now, if I didn't show you the t-distribution with the normal distribution overlaid, you'd probably say, well, that looks like a normal distribution, right? A peak in the middle, it tails off to two sides. But what it does is it tails off more gradually. It accounts for a little bit more likelihood that you get a extreme value than the normal distribution does. So there's still some chance of getting a value over here, whereas with a normal distribution, it pretty much goes to 0. And so it's like a little bit shorter, a little bit wider than the normal distribution. And so if we look at this table here, we can see that the t-distribution is affected by the sample size. The normal distribution, where we use z-scores, is not. So it's the same. It only depends on the mean and the standard deviation. But if we take confidence levels, so the 68, 95, 99.7 rule, z-score is 1, 2, and 3. Well, the t-score, if you have a sample of 10, goes to 1.053, 2.284, 3.957. So for the 68% level, it's about the same. Gets a little bit more significant here as we go to 95 or 99.7. So we're basically using a 4 instead of a 3. But then you'll notice what happens as you increase the sample size, the values get closer to what we expect from the normal distribution. So it's 1.005 when you have a sample of 100. It's 2.025. It's 3.077. So the bigger the sample, the less important this is. But when you have a small sample and you're estimating both the mean and the standard deviation from the sample, then you should really be using the t-distribution that accounts for that extra uncertainty in the estimations. Okay, so let's apply this to the previous example. So we'll come back to our example. Now we're going to use the appropriate t-score instead of z-score. So go back to this table just quickly. We have a sample of 100, and we want the 95% confidence level. We were using a 2, but now we want to use 2.025. So we're just changing that one number. This is still our sample standard deviation, sample size. And so instead of just adding and subtracting 0.2, we have to add and subtract 0.2025 to get our true 95% confidence interval. And so the numbers don't change appreciably in this case because our sample is 100. If our sample was 10, it would be a little bit more significant. But regardless, the t-score is the correct score to use here when you have an estimate of both the mean and the standard deviation. We essentially get the same answer. You know, if you were rounding this is 1.8, 2.2. But in situations where you really care about those extra decimal places or you have a particularly small sample, it will make a significant difference whether or not you use the z-score or the t-score. So just by default, if you're calculating a mean or calculating a confidence interval for a mean, and you're estimating both the mean and the standard deviation, when you calculate the confidence interval, use the t-score.